Is light really the ultimate speed limit of the universe? For more than a century, every experiment has pointed to the same answer. Nothing moves faster than light, about 300,000 kilometers per second. But the deeper physicists looked, the stranger the rule became. Because the universe doesn't just set this limit, it enforces it. The closer anything gets to the speed of light, the more reality begins to fight back. Time slows down, energy requirements explode, space itself starts behaving differently. And physicist Richard Feynman once pointed out something even more unsettling. This limit may not exist to stop fast travel. It may exist to protect the structure of reality itself. Welcome to Simulation Hypothesis. This is where we question the grand promises of space and examine what the physics actually allows. No hype, no fantasy, just the reality hidden behind the beauty. If you're new here, subscribe and stay with us, because sometimes the most fascinating discoveries in physics are also the ones that quietly define the limits of reality. The speed of light is often introduced as just another number in physics. About 299,792 kilometers per second. Fast enough to circle Earth more than 7 times in a single second. Fast enough for sunlight to cross the enormous distance between the Sun and Earth in just over 8 minutes. But in modern physics, this number is not simply a measurement. It is a boundary. Everything in the universe, matter, energy, signals, and even cause and effect appears to obey it. And the strange part is that scientists did not design this rule. They discovered it. At first, physicists did not expect light to have a fixed speed at all. In the 17th century, Isaac Newton believed light traveled instantaneously. Many scientists agreed. Space seemed empty, and if nothing was there to slow light down, why should it take time to move? The first serious hint that light had a measurable speed came from astronomy. In 1676, Danish astronomer Ole Romer was studying the orbit of Jupiter's moon Io. Io regularly passes behind Jupiter, creating predictable eclipses visible from Earth. But Romer noticed something strange. The timing of these eclipses changed depending on Earth's position in its orbit. When Earth was moving away from Jupiter, the eclipses appeared slightly late. When Earth moved closer, they appeared earlier. The difference was small, minutes at most, but the pattern was clear. Romer realized the delay was not caused by the moon. It was caused by light itself taking time to travel across space. For the first time in history, scientists understood that light had a finite speed. But they still did not realize how important that speed would become. By the 19th century, experiments began measuring light's speed directly. In 1849, French physicist Hippolyte Fizeau performed one of the first terrestrial measurements using a spinning toothed wheel, and a beam of light reflected several kilometers away. A few years later, Léon Foucault improved the method using rotating mirrors, achieving even more precise measurements. Again and again, the number converged on roughly 300,000 kilometers per second. At that point, light's speed was just another property of nature, interesting, but not fundamental. Then something unexpected happened. Physicists discovered that light's speed did not change, even when the observer was moving. And that result made no sense. Imagine standing beside a highway watching cars pass. If one car moves at 100 kilometers per hour and another moves at 120, their speeds are relative. If you begin driving yourself, the speeds you measure change depending on your own motion. That's how velocities normally behave. But light refused to follow this rule. In the late 1800s, physicists Albert Michelson and Edward Morley conducted one of the most famous experiments in science. They were trying to detect Earth's motion through something called the luminiferous ether, a hypothetical medium believed to carry light waves through space. If Earth were moving through this medium, then light traveling in different directions should have slightly different speeds relative to Earth. But when they performed the experiment in 1887, the result was shocking. The speed of light remained the same in every direction. Earth's motion did not seem to affect it at all. The ether could not be detected. and the experiment produced what physicists called a null result. Nothing changed. This result confused scientists for decades. Because if light's speed stayed constant regardless of motion, it meant something fundamental about space and time had to be wrong. Then, in 1905, a young physicist working in a Swiss patent office proposed a radical idea. His name was Albert Einstein. Einstein suggested that the speed of light was not just another velocity. It was a universal constant. No matter how fast you are moving, you will always measure light traveling at the same speed. And if that statement is true, something else must change instead. Space and time themselves. Einstein's theory of special relativity revealed a strange consequence. As objects move faster and faster, approaching the speed of light, time for those objects begins to slow down relative to outside observers. This effect is called time dilation. At everyday speeds, the effect is tiny, but at extreme velocities close to light speed, it becomes dramatic. Astronauts traveling near light speed would experience time passing more slowly than people on Earth. But that is only part of the story. Length also begins to change. Objects moving at relativistic speeds contract along the direction of motion, a phenomenon known as length contraction. And mass, in a sense, begins to resist acceleration more strongly. The closer an object gets to the speed of light, the harder it becomes to push it faster. This leads to one of the most famous conclusions in physics. To accelerate an object with mass to the speed of light would require infinite energy. Not enormous energy. Infinite energy. And infinite energy does not exist in the physical universe. This is why nothing with mass can reach light speed. No matter how powerful the engine, the closer you get to that limit, the more the universe pushes back. Energy requirements rise faster and faster. Acceleration becomes harder and harder, until progress effectively stops. The speed of light becomes a wall. But the deeper implication is even stranger. Light itself travels at this speed not because it is special, but because it has no mass. Particles without mass, such as photons, are not slowed by inertia. They exist at the maximum speed the universe allows. And that speed seems to govern more than just motion. It governs information. In physics, information cannot travel faster than light. If the sun suddenly vanished, hypothetically, Earth would not feel the gravitational change instantly. The effect would propagate outward at the speed of light. Even gravity obeys the same cosmic speed limit. This rule ensures that events unfold in a consistent order across the universe. And that consistency matters more than it first appears. Because if something could travel faster than light, the consequences would be deeply unsettling. Imagine sending a message faster than light. In certain reference frames, depending on the observer's motion, that message could appear to arrive before it was sent. In other words, faster-than-light travel opens the door to backwards causality. Effects appearing before their causes. Messages arriving before their transmission. Events influencing the past. This isn't science fiction speculation. It emerges directly from the mathematics of relativity. And physicists have explored these paradoxes for decades. This is where Richard Feynman, one of the most brilliant theoretical physicists of the 20th century, offered a fascinating perspective. Feynman was famous for his ability to explain complex ideas with disarming clarity. When discussing particles and relativistic motion, he sometimes described certain processes in quantum electrodynamics in ways that seemed almost paradoxical. In one interpretation, a particle moving backward in time could be mathematically equivalent to its antiparticle moving forward. This idea was part of how Feynman visualized particle interactions in what became known as Feynman diagrams. These diagrams became one of the most powerful tools in modern physics. But they also hinted at something strange. If the speed of light barrier were broken, the neat ordering of cause and effect could collapse into contradictions. Particles appearing before they exist. Signals influencing events that have not yet happened. And physical laws rely heavily on the idea that causes come before effects. Break that rule, and physics itself begins to unravel. That realization led many physicists to suspect that the speed of light is not merely a practical limit. It may be a structural rule of the universe, a boundary built into space-time itself. The universe does not simply discourage faster-than-light motion. It reshapes time, energy, and space to prevent it. The closer anything gets to that limit, the more reality bends to stop it. And this raises an even deeper question. If the universe works so hard to enforce this boundary, what would actually happen if something somehow crossed it? Once physicists accepted that nothing can exceed the speed of light, a deeper realization followed. The speed of light is not just about light. It is about how the universe organizes events. To understand why, imagine two events happening far apart in space. A star explodes in one region of the galaxy. Somewhere else, a spacecraft launches. If these events are separated by a large enough distance, different observers moving at different velocities may disagree about which event happened first. This sounds strange, but it's a natural consequence of Einstein's relativity. What all observers must agree on, however, is causality, the relationship between cause and effect. If one event causes another, then every observer must agree on their order. The cause must always happen before the effect. And this is exactly where the speed of light becomes crucial. Because the speed of light defines the maximum speed at which cause can influence effect. In relativity, physicists describe this with something called a light cone. Imagine a flash of light occurring at a single point in space-time. The light spreads outward in all directions, forming a cone that expands into the future. Everything inside that cone can be influenced by the original event. Everything outside it cannot. Not yet. If information could travel faster than light, it could jump outside the light cone. And that's where things start to break. Because outside the light cone, the order of events becomes ambiguous. For one observer, event A might happen before event B. For another observer moving at high speed, event B might appear to happen before event A. Normally, this doesn't cause a problem, because if the events cannot influence each other, the order doesn't matter. But if faster-than-light signals were possible, suddenly cause and effect could swap places depending on who is watching. And that creates a paradox. Imagine sending a faster-than-light message. You send a signal from Earth to a spacecraft moving away at extremely high speed. Because the signal travels faster than light, it reaches the spacecraft almost instantly. Now the spacecraft sends a reply, also faster than light. But relativity allows certain frames of reference where that reply could arrive before the original message was sent. The result is absurd. You receive the reply before you even press the send button. This is sometimes called a causal loop. And causal loops allow situations where events influence their own past. For example, you could theoretically receive a message from the future telling you not to send the original message. If you obey the message and never send it, then how did the message arrive in the first place? The logic collapses. This kind of contradiction is known as the grandfather paradox of faster-than-light physics. And physicists take these paradoxes very seriously, because physical laws must remain consistent. This is one reason many scientists believe the speed of light is not just a practical barrier. It is a causality barrier. Break it, and the universe may no longer have a consistent timeline. And this idea appears again and again in theoretical physics. Even in situations where faster-than-light motion seems mathematically possible. Take tachyons, for example. Tachyons are hypothetical particles proposed in the 1960s that would always move faster than light. According to the equations of relativity, such particles could exist mathematically. But they would behave in bizarre ways. If tachyons lost energy, they would actually accelerate instead of slowing down. If they gained energy, they would slow toward the speed of light but never drop below it. More troublingly, tachyons would allow signals to move backward in time. For decades, physicists searched for evidence of tachyons. None has ever been found. Most modern physicists suspect they cannot exist in reality. because if they did, causality could collapse. Even more exotic ideas have been explored. One of the most famous is the warp drive. In 1994, physicist Miguel Alcubierre proposed a solution to Einstein's equations that would allow a spacecraft to travel faster than light, without technically moving through space faster than light. Instead, space itself would move. The idea was to compress spacetime in front of the spacecraft and expand it behind, effectively carrying the ship along a warp bubble. Inside the bubble, the spacecraft would remain stationary. But the bubble itself could move faster than light relative to distant observers. At first glance, this seemed promising. But the problem appeared almost immediately. The energy required to create such a warp bubble would be astronomical. Early estimates suggested it would require energy comparable to the mass of entire planets. Later refinements reduced the estimate somewhat, but the requirement remained enormous. And there was another problem. Warp bubbles might also allow closed time-like curves, paths through spacetime that loop back into the past. In other words, even warp drives threaten causality. Then there are wormholes. These hypothetical tunnels through spacetime could connect distant regions of the universe. If stable wormholes existed, they could allow travel between two distant points faster than light would normally take. But again, the equations reveal a problem. A wormhole that allows faster-than-light travel could also become a time machine. Physicists Kip Thorne and Stephen Hawking studied these possibilities extensively. Hawking eventually proposed something he called the chronology protection conjecture. His idea was simple. The laws of physics may actively prevent time travel in order to protect causality. In Hawking's words, the universe may have a mechanism that prevents the appearance of closed time-like curves. In other words, the universe might protect its own timeline. This brings us back to the strange idea hinted at by Richard Feynman. In relativistic quantum theory, certain particle interactions can be interpreted as particles moving backward in time. Feynman famously described antiparticles as particles traveling backward through time in mathematical diagrams. These interpretations were never meant to imply literal time travel, but they revealed something profound about how the equations behave. At very deep levels of physics, the difference between forward and backward time becomes surprisingly subtle. That is why the speed of light boundary matters so much. It keeps those strange mathematical possibilities from spilling into everyday reality. Because once you cross that boundary, the universe loses its ability to maintain a consistent timeline. Events could influence their own past. Information could appear without origin. Cause and effect could reverse. And if that happened, physics would lose its predictive power. Science depends on the assumption that causes lead to effects. Break that assumption, and the entire structure of physical law becomes unstable. So the speed of light does something extraordinary. It preserves the order of events in the universe. It ensures that information spreads at a finite rate. It prevents signals from outrunning causality. And it protects the universe from paradoxes that would otherwise tear logic apart. Which leads to a fascinating conclusion. The speed of light may not simply be the speed of light. It may be the speed of reality itself, the maximum rate at which the universe can transmit cause and effect, a boundary written directly into the structure of spacetime. And every time scientists try to imagine breaking it, they run into the same wall. Not just technological difficulty, but logical impossibility. Because if something could truly outrun light, it might also outrun the rules that keep the universe coherent. And that may be the real reason the universe fights so hard to stop it.